So the revised schedule for this afternoon, I believe, is 2 talks. First by Bernard Schutz and then by Roberto Dolcetta. So we'll start with Bernard. Hearing is believing. Lisa as a black hole monitor.
Right, thanks. This was originally meant to be this morning, and the reason we postponed it was that I've got some films and so on with some sound, and sound wasn't available this morning in the other room. It does mean, however, that it comes out of order. So this is more meant as a kind of cheerleading talk than a talk with any new results. The new results are already starting to come out in the other talks that we heard. But I wanted to address a particular question, which is where do we stand with Lisa now, and what are we going to be doing over the next few years and so on. So that's the theme of the talk, and it's particularly focused on the black holes, the supermassive black holes. Parallel to this is a set of questions that Pau circulated that are themes for discussion in the parallel sessions. I think a very comprehensive set of questions. I want to pick out basically a few of those and talk about what I see as their scientific importance and their future for their immediate future for understanding and moving the LISA project forward. So it's the analogy with sound. LISA, like other gravitational wave detectors, I think we're coming in this field to understand it has there's a paradigm, which is that it's not appropriate to talk about LISA seeing black holes, but rather listening to black holes. That is, our data set is just a 1D data stream, just like an audio stream. Our detectors are essentially omnidirectional, they're not pointed. And our spectrum is very broad. So LISA has 10 octaves of good sensitivity, and that's very unusual in any electromagnetic kind of astronomy. It's much more analogous to the spectrum spanned by our own ears and our own built-in audio systems. So the analogy with listening is a good one. It's being developed, I think, by a number of people. And it does condition, in some ways, how we talk about LISA, how we fit it into the observing program in astronomy, the complementarity of gravitational wave detection with other branches of astronomy, I think are all easier to understand if you think about the analogy with sound. And in particular, I want to show, some of you have seen some of these clips already if you were at Stanford and heard the public lecture I gave. So I apologize if it's repetitive, but I just want to illustrate what is it like to see the universe optically, and then what is it like if we're going to add the soundtrack that LISA has. So here's the universe optically. The universe is a jungle, as we all know. But all we do is we see it. But then if you play the same sequence with sound, there's just a lot more in the universe. There's just a lot more that your attention is drawn to. And you want to investigate because you can't even see these things in the beginning. That's your unexpected source. That's the LISA discovery space. So that's what life would be like without sound, and in a way that's what we're trying to do. We're bringing sound into our observations of the universe. And also another way of making this another point to this analogy is the whole question of how do we find directions. This is something that's unfamiliar with all gravitational wave detectors. The ground-based gravitational wave detectors find directions through basically triangulation. Basically, the signal arrives at one detector before it arrives at another, and then you triangulate on the sky, and that is also something our ears use in order. That's information our ears use in order to locate things. But LISA doesn't do that very much because LISA's detectors are all in one spot. At high frequencies, that helps a bit. The main way LISA will tell directions is through the Doppler effect, and there's another film I have that I can use to illustrate that. So here we're on a train, and you can hear in the background the bell of the crossing. So if you're on the train and you want to know when do you pass the crossing, the windows are closed, the shutters are down, you're listening but you can't hear, when are we going to cross this road where the bell is? It's just now, right? And that's the crossing. So that's information our brains use in order to locate sounds, that is change of pitch, and that's exactly what Lisa's doing. We're going to pass some black hole binary system and watch the change of pitch. It's not quite so dramatic because we're not so close to it and we're not going in a straight line. We're going in a circle with Lisa, and so we have that information building up with time as to where that location is. But it's basically the same kind of effect. And so the final thing I want to play for you is the whole LISA soundtrack. That is, what we're doing the MLDCs, the Mock-LISA Data Challenges, and we're making simulated LISA data sets. And so I've taken one of them. I think it's an early one. I think it's the training set for Challenge 2. Made it into an audio track that we can listen to, and that involves raising it in frequency by, I think it was 19 octaves, I'm not quite sure. And fortunately that compresses it in time, so we can listen to a whole year's worth of LISA data with, so I hope this is loud enough for you to hear. That's at redshift 1. A couple of black holes at redshift 1. Loud. I haven't faked this. This is just MLDC. All of this stuff in the background, all these binary systems in the galaxy.
You're not getting like a hiss load going, right? You're getting.
There's not enough of them.
You're just hearing mostly the a few bright guys making like the bagpipes.
Yeah, that's right.
Yeah, you can hear distinct pitches. You can also
Now you
hear
can-
rhythmic patterns.
You can hear another coalescence building up. And after this one comes, listen carefully if it's loud enough. Maybe. And now. Did you hear that one? That was further away. I think maybe at redshift 2 or something like that. There were 3 coalescences in that training set. And what you learn from that, of course, is it's audible for a long time. So we're getting the signal. We're starting to figure out what the parameters are, what the location is on the sky for months ahead of time. Right. And as Neil says, the real data, if I digitized, if I did the same thing with a better training set, we'd have much more of a hiss from the background because there's so many that it's binaries, that it's really a noise. This one, however, for PR purposes is a lot better. This is, if you can convince people that this is what it sounds like, it's
Can't hear the Emrys though, right?
Pardon?
Can't hear the Emrys.
You can't hear the Emrys, and that's right. That data set had a lot of EMRIs in it, and you can't hear them at all. So you need the matched filtering to go down for the EMRIs, and you have to subtract out, and that's really important. Those loud signals have to be subtracted out in order to be able to get down to the EMRI levels. So that's why we're doing the challenge, and we've got a lot more to learn about that. So this talk is about hearing and seeing. So we're going to have two ways of looking at the universe. One is listening to it through Lisa, but of course the other is all the different ways in which we can see the universe with different kinds of electromagnetic astronomy. So that build-up of signal means that we get a lot of information, and one of the kinds of information that builds up is the position information. And this is going to be particularly important for the interaction with other fields of astronomy. And so the thing that is really striking about this is how the position, so this is the position improvement days before merger. So time runs this way, and that's the position in arc minutes. So here's 100 arc minutes, a bit bigger than a degree, and 10 arc minutes down there. And these curves are different kinds of sources. So there's a pair of 10 to the 5 solar mass black holes. This one goes down to, this is 10 to the 6 and 10 to the 5. It's the same thing here for different kinds of sources, 3 times 10 to the 6 and 10 to the 6. So there's a whole bunch of different possible pairings of massive black holes. But they all follow the same trend, and they're all in roughly the same sort of region. Early positions of the order of 1.5 degrees or 2 degrees. Late positions go all the way down to, this one is below 20 arc seconds, or arc minutes rather, and all of them terminate in that very nice region. So we go down to sub-degree level for practically any of these binaries. These are all at redshift of 1. Obviously it degrades with redshift, but these are at redshift of 1. Now, the striking thing about this is this cliff. It's gradually improving, as you would expect, but then on the last day, this is 7 days, 14 days, so on the last day it goes plummeting down. Now the reason for that is that we've put into the, we didn't know about that when we first proposed LISA, we didn't know about that in the early days of LISA. We've put into the signal by this time what are called the higher harmonics. So in the LISA signal, in the signals emitted by black holes, you have the in spiral, and you have for a long time we just used the sort of standard post-Newtonian signal coming from the in spiral, which just had the quadrupole radiation in. But we know from the higher corrections in the post-Newtonian that there are nonlinearities that lead to harmonics above the quadrupole, second, third, fourth harmonics. And they contain a significant amount of information, but they are radiated because they're relativistic corrections. They're at the end of the post-Newtonian spiral. So they get stronger and stronger at the end. And when you add that to the general increase in signal noise, because the energy is coming out more and more rapidly at the end as well. So when you add that to the increase in signal noise, you get this dramatic improvement in positions on the last day. So what it means is that in interacting with astronomers, we have relatively large error boxes, but then at the very last, on the very last day, we can pin down the sources.
Everything you said was true just then, except it's not that paper. That was spin. And you get the same effects from higher harmonics.
Yes,
there
that's
the
right.
resolution was coming from the spins. They had no higher harmonics in that.
I thought the spin.
Well, the spin is
spin
putting in,
was,
spin precession.
yeah.
So this is spin precession.
This has
but
been.
this does not include the higher post-Newtonian harmonics, but they have the same. They do the same thing of getting a very fast thing at the end, because of course
Put in the higher.
those are highly relativistic terms, and those only come in and break degeneracies right at the end. So everything you said is true, but not actually that paper.
But it's not actually in the.
Do they
Yeah.
drop to this small?
But the higher harmonics.
If you have perfectly aligned binaries?
You pretty much you get much the same sort of effects happening from the higher harmonics. Yeah, and when you put the two together,
The higher harmonics are independent of that.
yeah,
Yeah. All right. Sorry. Yeah.
yeah.
And the fact that there's this universal power law they're all following is a combination of just the power law in gravitational radiation plus noise scaling, and if there's a break because you're dealing with.
It's a breaking of correlations that happens.
Yeah, that's right.
Right, so up until this point, there are correlations in the parameters, and you're just improving the signal to noise. Now you are getting a blast of signal to noise, but you're actually adding no additional real positional information at that moment because Lisa barely moves in the last day. It's actually the breaking of degeneracies then which allows you now to sort out what's going on. So it's the degeneracies between various parameters that get broken by these effects, and these are highly relativistic effects. So you only get that information the last day. But they actually, what they're doing is they then allow you to make sense of the information from a year earlier. That's effectively what's sort of happening.
Lisa, even without even in short observations where you don't have the long-lasting integration time to get positional information, you do get position information in the last, comparable position information just from looking at the last part, particularly when you include the final burst with the numerical relativity parts. But,
Yeah, and the higher harmonics make a big difference because they improve your telescope's resolution. You're basically dealing with a shorter wavelength of the baseline.
the positional information comes from the fact that the sensitivity depends on the frequency, not just the.
It's really triangulation in the case. At high frequencies, you can think of it
You can
as
think of it as a
pulses
time delays,
triangulating at the free space.
Anyway, this is what we expect.
It's an informal meeting, but it's going to happen.
So my question is, what happens in astronomy when this sort of thing is developing? And we're listening to the LISA soundtrack, and we hear this black hole about to coalesce. So what happens is not something we can predict right now, because I don't think we've given enough attention. We're starting to give a lot of attention, but certainly there's a lot more to be done on questions like counterparts, afterglows, preglows, available galaxy surveys. So if we have a catalog, for example, of all the galaxy, all the active and disturbed galaxies out to redshifts of order 1 by that time, then identifying possible candidates will be a lot easier. But these are questions that are going to be addressed here, but also questions that need to be addressed in the future.
Quick question.
Yeah.
Within that sort of distance, so 10, 20 odd minutes, how many galaxies are there typically that are massive enough to contain two black holes of the sorts of mass we're talking about here?
I think still at redshifts of 1, in that angular position, you expect a whole cluster. I don't think you're down to resolutions between galaxies. I think you might be able
Thousands.
to separate
Yeah.
clusters.
Thousands, tens of thousands.
Yeah. You have just
But
a
none of that
handful
mass,
clusters.
No, that was my question, right? So
But these are not massive.
That's what occurred to me.
This
right?
is the
If
10
you
to
look
the
at
6, 10 to the 7, so much
Yeah.
the body. It's not massive galaxy.
yeah, but if you're thinking of like
AGN.
AGNs of that luminosity, how many would be? I mean, that was
Yeah.
first, I forget which paper it was, but the numbers vary between like 1s to hundreds depending on the.
But you're really looking at starburst
Yeah,
Yeah,
galaxies.
for a pair of 10 to
Yeah.
6 solar mass black holes, this is nothing very special.
No, no.
Well, it depends upon the masses, but that's one of the things that we have to understand. But if they're still in starburst activity because of the recent merger, then you have a chance of picking them out. We're not talking about 10 to the 9, 10 to the 8, 10 to the 9 solar mass black holes. We're talking about 10 to the 6. So I've broken, the rest of my talk is just, I want to develop, as I said, a list of questions that we want to, that I think we should be interested in. And it's particular because we do have a distant launch window still for LISA. Optimists would say we might have an opportunity if things go right and some obstacles fall away for a launch around 2020. The Cadle survey said 2025, and even if you had a launch date today of 2020, you might think that 2025 might be more realistic. Somewhere in that time frame, and that's still 10 to 15 years. So what's the point of talking about LISA? What are we supposed to be doing in between? What's interesting? What's enough to capture the interest of astronomers and kids? And keep research on these active. That's something that a lot of us have been asking questions about. And so I have a private list. Pierre and I actually were looking at this some extent, but this is my own private list of what I think is interesting, anyway, in different parts. So this is the astronomers list, then I have a list for relativists on the next slide. But first, one of the things that's very active right now is counterparts to mergers. Can we identify those galaxies in which the merger took place? And it's questions like starburst that we've just been talking about. We need more simulations of what happens with wet and dry mergers. We need more physics in those simulations. We maybe have to bring in questions of do certain kinds of mergers or certain kinds of activity lead to jets or other MHD phenomena. We would like to have sharper predictions than we have now, and all this I'm sure is going to take place as we get more research in counterparts. The EM wavebands, the other EM wavebands is something I'll come back to in a minute. But I think it's also important to remind ourselves that these mergers that LISA is going to be detecting are actually happening right now. Unfortunately, LISA is not up there and identifying them. So we don't know exactly when they're happening. But, and importantly, we don't even know which half of the sky they're in, let alone, anything else. So the question is, can we observationally develop a program to pick out candidate galaxies in which these things are happening now, this year? There's one or two at Redshift 1 this year that are happening. So where are those galaxies? Can we identify those galaxies? Can we use the counterpart simulations to look for galaxies? And if it was 20 years, if it takes 20 years for the counterpart to brighten up, well, find the ones that happened 20 years ago. It may well be that there's a sensible observing program, particularly as we get more and more monitor programs, transient monitor programs. And that's really interesting to try to match the predictions, and this goes back to the earlier thing about other EM wavebands, match the predictions when we talk about counterparts, match them to the available transient monitors that are operating now. And we have transient monitoring in the radio with low frequency radio, particularly LOFAR is now in operation. Obviously we have gamma ray bursts and capability of seeing X-ray transients, and there's a lot of supernova surveys and lots of pictures of the sky being compared with pictures taken a week earlier and things like that. So if we could match counterpart predictions to some of the existing surveys, we may just be able to do some data mining and find out maybe some of these things actually happening now. To understand this, understand what the counterparts are going to be, understand the rates of events that we might expect, and help prepare for the data analysis and so on, we certainly need continued population modeling, further investigations of eccentricity for different mass ratios, and just the populations of different mass ratios. Another thing that is really important on the astronomy side is this weak lensing issue, because weak lensing is the primary error source for LISA's luminosity distances. And that affects not only the information we can learn from those luminosity distances, from those standard sirens, but it also affects how easy or difficult it's going to be to identify the host galaxy, because if we get a distance, we don't want it to be one with a great deal of depth. So the smaller the error box, the better. So one way that people have suggested of improving the situation with the weak lensing, the effect of weak lensing is that it produces a random magnification of the galaxies. You have a certain amount of magnification with each encounter, and there are lots and lots of encounters. So you the distant apparent luminosity of the gravitational waves is affected by this lensing. So we don't get the right brightness. So if we could model a field of view around position, the known position of the source, if we could model the lensing, the weak lensing, could we gain somehow? Could we remove some of this effect? Maybe even factors of 2 or 3 would be a significant improvement. And are there synergies in talking about this program with ground-based weak lensing studies, ground-based studies that are primarily aimed at dark energy programs, and in particular with WFIRST, our partner in the Astro-GR 2010 decadal review. So are there things that, if WFIRST flies, are there things that we can get from its measurements that would allow us to remove some of this systematic distortion of our distances? So I think those are just a few questions, but I think they're high priority and all of them challenging, and therefore they're things that we, even with a launch date that's 10 or 15 years away, they're things that it would be very good to be understanding soon. Now I'm going to make a similar list for those for the relativity theorists. The EMRI, the extreme mass ratio, and the IMRI, intermediate mass ratio problems are not fully solved. So in the LISA waveband, those are 10 solar, the EMRIs are sort of classic 10 solar mass black holes falling into 10 to the 6th, and the IMRIs are intermediate mass black holes of, let's say, 10 to the 3 solar masses falling into a 10 to the 6th. The difference between them from the relativity point of view is the mass ratio affects how you address the problem. And the problem is that we have to make a good prediction of the signal. In that soundtrack that I played, there was no evidence of the EMRIs. They were there, but you couldn't hear them. You have to pull them out from the noise, and therefore you have to match the signal very, very well and over a lot of cycles. So that's a problem of solving the equation of motion. It's a problem of solving the two-body problem in general relativity.
Quick question, sorry, just remind us, or just remind me, everyone probably remembers this. How long is that signal going to be audible, so to speak, for in the LISA mission?
It could be audible for years. It's certainly audible for a good, better part of a year. Yeah. Oh, that's right. There's some systems that we probably could be tracking.
So we could be having to disentangle a great number of these, then, actually.
Yeah, they don't have any overlap with each other, basically. I mean, they just don't sound like each other.
Each one is quite individual, although they move through the band, through the whole LISA band, but they're not all at the same frequency. They all have basically a narrow band, narrowish band sort of structure, but it's moving through the whole band. I don't know what happened. So the problem is challenging from the relativity point of view, because there's 10 to the 5, 10 to the 6, or more cycles that you have to model. Although, in order to detect these things, you may not have to be that good, but still, we have not yet got to the point where we could actually pull out real signals. So we have the confidence that we today, if LISA were flying, we could pull out real signals. So if Oliver, is Oliver? That's good. Oliver's on a telecon. He's not in the audience. I will say that it's not a bad thing that LISA is delayed, because if we stuck to the original launch date of LISA, which would have been this year or 2 years from now or something like that, we would not be in a position to detect these signals with nearly the sensitivity that we need. Yes, that's also true. There speaks as a guy who feels he's starved of resources to attack the
That's
problem.
another question then. So in a technical sense, with the LISA-like mission, do we, so to speak, keep everything, and then so 20 years later,
Sure.
something will come up?
Yeah, that may well happen. I mean, that certainly will happen. We'll keep everything, and it may well be that we'll learn
Well, I
things
mean,
in the
so
future.
in terms of being downloaded, so for example, let's say Gaia as a mission where lots of things on board is compressed.
No, everything will be kept.
Yeah.
The data rate is very low.
So if we figure out how to analyze it 30 years later, that's fine.
Yeah. You'll be able to put all the LISA data on a memory stick. Carry it around with you for your next big inspiration. The problems that we have to address, the theory problems, are different for these different kinds of sources. So the first bullet there is EMRIs. People like Leor have been doing perturbation theory for in general relativity. That is first order perturbation in the mass ratio, which is 10 to the minus 5. So that's a small number. So basically the small object is a perturbing, creates a perturbing gravitational field in the background of the large black hole. And you have to look at the back reaction effects in that perturbed system, because the only reason that the small object falls into the black hole in the first place is it has its own gravitational field that's radiating gravitational waves. If it was a pure test particle, it would just follow geodesics all the time. So you have to calculate the gravitational field disturbance produced by the small mass, and then calculate the radiation and calculate the effects. But the effects on the orbit are not just that it's losing energy and angular momentum. There's extra precession effects. There's also lots of non-radiative effects, and so the equation of motion, and they all affect the waveforms. The equation of motion is quite complicated. So in principle, now I think it's fair to say that in principle the perturbation problem is under control, but we have still difficulty calculating the orbit, because it's a massively challenging problem, particularly around in the Kerr metric, particularly when we don't even have spherical symmetry. And that's where, of course, the problem is much more interesting. So we're still some way away from getting signal predictions. Nevertheless, the problem is in theory under control. If I go up to the intermediate mass ratios, where the ratio might be 10 to the minus 3 instead of 10 to the minus 5, perturbation, first order perturbation theory may not be adequate because that number is a bit bigger. And if we're going to track the signals all the way through the LISA band, we may have to go to second order perturbation theory by the time we're close to the horizon. So that's one way of addressing that issue. And that problem isn't at all under control. That problem is something people are starting to think about. So right now, we could probably identify an IMRI signal, but we couldn't track it all the way to the end. We couldn't extract all the physics information from it. Another way of attacking it, of course, is to use numerical relativity. We are already integrating massive black hole mergers through numerical relativity. If I'm really interested in the end point, the last few cycles and so on, in the IMRI case, maybe I should do that with numerical relativity. Problem there is that, again, the present numerical methods they sort of have difficulty getting you beyond a mass ratio of 10 to 1. They certainly wouldn't go to 100 to 1 or 1,000 to 1, which is really what we're interested in.
There was a paper a couple of weeks ago, I think, by Carlos Lusto, where they claim that they're now making 1 to 100.
This was from a group in China.
No, Carlos.
By-
Carlos Lusto.
Oh, Lusto. Okay.
Yes.
But with massive, it's brute force.
100, only the last two orbits.
Yeah, the last two orbits and so on. So we need better. So to attack this, we need better methods. We have to do something differently about the numerical methods. The reason is simply that it's a resolution problem. The smallest scale is this small black hole, which is doing nothing. But basically, you're integrating it and creating it every time step. You run out of resources quickly, and as our computers get better and better, we can just raise the mass ratio that's interesting and make it still impossible. So I think we certainly need different approaches if we're really going to be able to join on numerical methods for sort of moderate mass ratios with these perturbation methods. or maybe there's something else that I haven't thought about that we could do. But even in the case where we have comparable mass mergers, which we can treat with numerical relativity, we're very happy to produce waveforms by patching together an in-spiral from post-Newtonian and then the final 10 orbits or something with numerical relativity. But all we're doing is patching the waveforms together. And that's going to be okay for the kinds of signals we expect to detect with ground-based detectors over the next 5 years or so. But by the time LISA comes in, we're going to have high signal noise measurements of these systems. And I think if the signal noise goes above about 100, the present methods just aren't going to be able to represent the whole waveform accurately enough to measure parameters, that is, to be able to measure the masses and the inclination and all the other things you want to measure from this system. The reason is that we don't start off in numerical relativity with the right initial data. We start off numerical relativity with convenient initial data, but it isn't the real state of the system, in particular the geometry and so on, are oversimplified. And we let things cook for a little while, and then we hope that they're pretty much okay, and then they join on. But I would say our representation of our ability to measure parameters, confidence in that, is probably not better than about 5 or 10%. Would the numerical relativists like to challenge me on that?
I think we'd do better than 5 or 10%.
Depends on what parameter.
But I would add here an important detail, which is that the parameter space that we need to understand is 9-dimensional to include centric systems. So we have very little progress in completely characterizing the parameter space, which is
Also
what you ultimately need. So
Yeah.
there's another big.
But I mean, for the astrophysicists in the audience, I mean, I wouldn't get too worried about this because, I mean, I agree with you that to really utilize and get down to the precisions that you could, in principle, get with LISA, you want to do this. But if you just truncate the signal, like literally just throw away everything from, 20 M onwards, right? Like when they've got within 20 M, just throw all that signal away. Then you've still got, for a typical LISA system, the masses measured to fractions of a percent, sky locations to, I mean, you can do great astrophysics with the measurements you get without even using the merger and ring down. So depends on what if you want to do tests of general relativity, you have to get this right.
That's why it's on this
Right.
page.
But as far as the astrophysicist is concerned, unless you really want to know the mass of the black hole, the parts in 10 to the minus 6, you don't really have to worry about
But
this
is that true for
You don't know
spins
what-
too?
Yeah.
You don't know what the physical initial data are for different types of So you can do simulations starting from some convenient initial data, but you don't know if the actual system is going to do the same.
Yeah,
I'm
so
talking
but
about
Neil is
stuff
saying throw
from-
away the numerical
As we just
relativity
discussed,
completely.
this
So there we have a good
Oh,
signal.
the last part.
Yeah, yeah. So the first part gives us.
Yeah,
No, you
so,
both, you both.
but you can't do everything, right? The
Not-
whole
not-
problem
not
is
if you throw away
degeneracy,
your
or we wouldn't have the, but no, if it were that good, we wouldn't have that plot you already showed. The problem is that it's the nonlinear, it's the harmonics and the spin
For
precession
the
for the
resolution,
end.
yeah, for the sky resolution to get it.
So
Yeah,
what's
so
spin?
there's a lot of information there in the numerical relativity for the astrophysics, but also a huge amount of information for tests of general relativity and so on. Stas?
I think I want to add, even before going to spins, I think there are still problems even for simple, non-finished partial black holes, because masses, just for example, two masses which are measured in Newtonian, but Newtonian theory, are not necessarily the same as what was with the attached in numerical relativity. So there is even problem, on the level of even doing stitching the numerical waveforms for Newtonian. There are a lot of questions there.
Yeah, this is what I was quoting at the 5 or 10% level. I don't believe that we, maybe 10% is too bad, but I don't believe that we actually know what the masses are to put into the numerical relativity simulation to a few percent level compared to the masses that are used in the parameterization of the in-spirals. I think we don't know how to match those.
Well, certainly for non-spinning, I think that the mass, the uncertainties related to the definition of the masses is not that great at all. Which we can kind of see from looking at the constancy of the apparent rising mass, which is our numerical standard, is extremely constant and can be can be connected based on a sort of comparison of energetics at the 10⁻⁴ level with the masses that you have from post-Newtonian. But maybe that was saying last slide. But so I don't think there's a big issue with masses, but there are subtleties in there that will need to be addressed, especially with the spinning systems.
Yeah. So that's probably okay. Yes. I'm being provocative, but I think not very far from the truth. If we really want to be able to extract the maximum information from the very strong signals that we're going to get with LISA, we need to match the post-Newtonian and numerical better. And I think what that means is we need to find out a way of starting off the numerical calculation with initial data that's inherited for the whole space-time, that's inherited from the post-Newtonian, and not just sort of parameterized masses. So I think there's no reason it shouldn't be done, but it raises all sorts of very messy questions in numerical relativity about gauges and things like that that are really hard to solve. So that's something that I think that has to be solved if we're going to get maximum information out of Lisa's observations. So my final list is for the data analysts in the room. What should we be thinking about? Well, it's no surprise we're already thinking about it in terms of MLVC, the generation of simulated data and trying to understand how to do the data analysis problem and recover signals and so on. So the immediate goal is really to do the whole thing, remove, disentangle everything, and accurately estimate parameters. And we're still some distance from that, but I think progress over the past few years has been very encouraging that this is something that we probably are going to be able to do. After we know how to do that, then we have to understand that in a real-life situation with LISA, we have to be doing something at least in real time, because particularly with coalescences coming up from time to time, we want to be able to sort of progress day by day our information, so keep refining things. And the interesting thing about the way LISA data analysis works is it's a comprehensive thing. The more data you have, the better you can extract every one of the signals that you thought you had extracted before. So you basically, in principle, could go back over the whole problem and resolve it every day a little bit better. Now, we're not going to do it that laboriously, probably, but it's an interesting challenge to ask exactly how that needs to be done in a real-world situation when LISA is flying. We have to know how to do that. And a very important thing, I think, is to put in more realistic noise models. Even though the detector noise is a small fraction of what happens in LISA, there are frequency bands in which the detection is signal noise limited, and that's particularly the EMRIs. And so if we had a better representation of the hardware, and we could understand what artifacts might come out, so we're not just simulating noise as Gaussian, then I think we'd have a more realistic data analysis. And one of the interesting things is we've been talking at the AEI, we've been talking with the Pathfinder group, and it may well be that we can take some of the housekeeping noise from Pathfinder and use that to generate mock instrumental artifacts in the LISA data. And a question that has been asked by a number of people, but certainly is so broad that it's something we should have more questions about and maybe more approaches to, which is we talk about LISA testing GR, and the nice thing is that it is of course going to confirm GR. But what if it doesn't? Do we know what's going to happen? We know how to handle that. And actually we don't. And the same question was asked in the late 60s and early 70s about solar system tests of general relativity, and the parameterized post-Newtonian formalism was the answer to that. And that was an interesting answer because the regime of solar system testing, weak fields, was an easier regime to parameterize. Here, we can't really parameterize all possible theories of gravity. And the problem is that if your theory of gravity is different, it may be that the way it generates gravitational waves is different. So it's not simply a question of, do I get more amplitude here or a couple of extra harmonics, but maybe there's twice as much radiation coming up from these systems, and they're going to spiral in twice as fast, and therefore you have to track that in the new theory. So to model things in a different theory is a real challenge because we don't have a space of theories. We don't have a parameterization of theories. Maybe there is such an approach, but for the moment, we can only approach this in a sort of almost in a yes/no sort of way. Yeah, general relativity failed, but now if I want to ask what is really the right theory, then I have to look for other clues in the data. And a particular question is from the EMRIs. One very clean test of general relativity is that there's a whole class of theories, but particularly general relativity, that there's a horizon. And that means at the end of the EMRI signal there is really an end. And if that signal doesn't end, if we're tracking a nice EMRI and it just keeps going when it should have crossed the horizon, it means there isn't a horizon. So what is there, right? Is there some sort of boson star? People have talked about things that could masquerade as black holes, or is there a naked singularity? How do we tell at the end of a merger of two massive black holes if cosmic censorship has been violated? And our numerical simulations are all giving us nice mergers with nice curved black holes at the end. But if something happens and we get a naked singularity at the end, how do we tell that from the gravitational waves? So there's lots of room here for asking tough questions about what to do with LISA. What do we conclude from LISA data if it shows that general relativity is fails? Okay, and then finally, I don't want to leave out the rest of astronomy. So I wanted to focus on supermassive black holes, and I talked about EMRIs and mergers. But there's a huge amount of other astronomy that LISA is going to be doing, and white dwarf binaries, that's another talk. But I just wanted to throw in a couple of obvious things. First of all, there's the Gaia mission, that's ESA's astrometry mission. It'll be looking at white dwarf binaries. It'll find a lot of them by proper motion studies and photometry. We'll have more verification binaries for LISA when that data set comes in, but maybe there's a lot more to be done from that data set in preparing for LISA. And just to throw in that we have talked for a long time about the possibility of detecting solar G-modes. Maybe there's other solar physics that we should be doing. Again, that's something people keep coming back to in a fairly superficial way, but it's something we shouldn't keep. We shouldn't ignore. We should keep in the back of our heads on it as a possible area of astrophysics for LISA. So I'll stop there.
We have lots of discussion already, which is good, but we have a few more questions. Yeah.
About electromagnetic transforms, do we have an idea? I mean, we're always thinking about coalescence, and you showed that the way that we hear it is a very fast signal. Is there any indication that the electromagnetic counterpart would follow this time scale, this time evolution, or is it just going on and nothing singular happens while coalescence happens? What proof do we have that there is something happening at the moment of coalescence?
So there have been talk about prompt electromagnetic signatures after the coalescence, but those are and if there's a big kick to the remnant black hole, it has a big disturbing effect. But those still happen on timescales of days or weeks. Isn't that right?
I'm going to be talking about this tomorrow morning, and I think the fair statement is the error bars are as wide as you'd like to make them, but some things might say.
So a couple quick comments and a question for consideration. In terms of the data to apply to supermassive black hole binary mergers for LISA eventually, I think we should consider the pulsar timing array stuff. So in the next several years, it should give us a wealth of data, maybe not just an overall background, but individual sources.
Yes. Very
In the theory point, for IMRIs, if you're talking about 1,000 to 1 or larger mass ratios, I would have imagined that you could just drop the merger and ring down because they're going to be much, much weaker signal contributions than the in-spiral due to the mass ratio. And then the question is, in terms of for IMRIs or IMRIs, yeah. In terms of the last point you made about data analysis, as you know, there's been consideration of this in the ground-based sense. You know, what if, for example, binaries are actually somewhat eccentric, or there's some different law of gravity that's applying? And the answer I've gotten in that stage is that that's what the burst group is for. If you can't do a match filtering, maybe you can get it with burst. Have people considered that in the case of EMRIs or IMRIs in the LISA context?
Yeah, I don't think so. I mean, I don't think we've ever talked about completely template-free detection because the regime we're working in, we're expecting so many cycles, I guess. But
for
For
IMRIs, not
to a
necessarily.
certain extent, I mean, one of the things that, I mean, the way that the burst search works for LIGO is you have multiple detectors, right? And with LISA, if you have all 6 links running, you can do much the same analysis. RAW is much weaker with a burst-style analysis than a template-based analysis, but you could be cognizant of strong things like big departures in a black hole merger. If that looked nothing like the numerical relativity predictions, there's enough signal to noise there that a burst type search could handle it if you have, but it would be more challenging if we only had a single signal channel, because how do you know then that it's not instrument related? But a lot of those techniques can be taken over if we have full 6 links.
I think it's a good question because inside the LSC, the burst group has developed some really powerful methods with based upon very short oscillating sort of snippets of a waveform, and they're challenging the in-spiral group now in terms of being able to detect signals. So we expect if we do get a signal from the in-spiral group that it should be seen by the burst group as well. So they're not that far away in sensitivity now. So I guess.
But
Yes.
what's the use case though? I mean, because for LISA it's not a problem of detection.
For the EMRI, it is.
Oh, but
It's for the last. It's for the merger phase, I think.
So you think about EMRIs that you see as a burst and not before as
EMRI, you're not going to get burst type techniques aren't going to work there.
I didn't put up cosmic strings, for example.
strings,
There are lots of things that you might imagine.
You really need raw signal to noises.
So Stas has been trying to bring.
Basically, with 6 channels is correct, but remember about laser noise, you need to cancel it, right? So independent data streams will be much less, you need to apply TDI. So therefore, it really should work for those type of signals much better than anything.
We do have 3 data streams, but they have correlated noise. So that's the thing. But we do have the Sanya mode. So
I guess it could be applicable, but
With the Sanyaf mode, you can.
but everything I'm down to go there.
But EMRIs are just too weak per cycle, really, for these type of
So
techniques.
maybe I should have put a burst search into my data analysis.
you get a burst. What's it good? I mean, for LIGO it's great because it's the first detection of gravitational waves. For LISA it's just something from somewhere.
A burst is what employs the next generation of physicists in trying to figure out what caused it. All these postdocs that you're writing off.
Sure.
And that's why we'll all have USB drives.